So this talk will be about vectors. Vectors have two parts to them. They have a magnitude, which is basically how big is it, and then they have a direction. So what angle is it going off at? So you can think about something like this. So we have a vector which has a magnitude of 8, and it is at 45 degrees. And that would be a vector, 8 at 45 degrees. You can also think about a car traveling at 40 miles per hour, heading north. That would also be an example of a vector. So a vector has two things, magnitude and a direction. So magnitude, how big it is, direction, what angle, what heading is it heading off at. So in terms of a vector then, we could look at giving something like my first one there, 8 at 45 degrees. Well, we could look at what is the x and y component of that vector. So if I were to draw that out, 8 at 45 degrees, it would be something that looks like that. That is 45 degrees. The magnitude of that is 8. And we can look in terms of the x and y component. And so in terms of those, I could drop this straight down. We got that this would be the x component. This would be the y. And to get those, we can use our trig functions. And so we would have that x is going to equal 8 cosine 45. See, this is the adjacent side, that is the hypotenuse. And then my y would be given by the sine function. And so we can get the x and y component of this vector by using our trig functions. So in terms of this one then, we would find out that 8 cosine 45 comes out to be basically 5.66. And the y component would also come out to be 5.66 for that vector. So given this, we can come up with the x and y component. And so then, of course, given the x and y component, can we come up with the magnitude and the direction? Well, if I look in terms of this example, we got that this is a right triangle. And so if I know these two, I can get this by using Pythagorean theorem. And then also if I know these two, I can get the angle by using the inverse tangent. So the magnitude will be given by the square root of x squared plus y squared. And my angle theta will be given by the inverse tangent of y over x. And that'll give us in regards to our particular vector. So let's do an example. So for example, let's say we have the point is 7, 12. I want to know the magnitude and the direction of this vector. So the magnitude will be given by the square root of 7 squared plus 12 squared. So again, that we can just plug in. And we found out that that will give us 13.89. And then our angle theta will be the inverse tangent of 12 over 7. And that'll give us an angle of 59.7 degrees. So in terms of our angles, we do want our angle to be a number between 0 and 360. So we want it in terms of a positive angle. And so, for example, what would happen if I now have this one and I want to get the magnitude and the direction. Okay? So let's say it's now going to be -4, 8. Right? So my magnitude, again, is going to equal the square root of -4 squared plus 8 squared. And so we can put that in. And that'll give us 8.9. And then our angle of theta will be the inverse tangent of 8 over -4. And the toy gives you an angle of -63.4 degrees. Right? But another thing here about the toy, however, is that the toy is only set up to give you answers in one of two quadrants. It either gives you an angle in the first quadrant, or it's going to give you the angle in the fourth quadrant. Okay? But let's look in terms of what we know about our point. We know that our point is a -4 up 8, so basically it's there. The angle the calculator gave me is -63.4, so that angle would actually be here. So the calculator gave me an answer that is in the fourth quadrant, but I know my point is actually in the second quadrant, and it actually would be lying here. So to get the correct answer, we need to take that angle and add 180. And so we get that our true angle is going to be 116.6 degrees. Right? So again, the calculator only gives answers in first and fourth, but we can check it against our point and make sure we get the right angle, which will be this one. Okay? So my vector has a magnitude of 8.9, and it's going off at an angle of 116.6. Okay? Well, in terms of vectors and how we write them, in terms of the notation used in your book, you got that a vector is written in terms of its x and y coordinates. So x, y, but now instead of parentheses, we now use those symbols. Okay? So we can have a vector, and so let's say we got vector u, which is given by 3, 4. And that's my vector. Okay? Well, in terms of vectors, we can do things like adding, subtracting, and multiplying them. So we can take a vector and multiply it by a constant. So the vector 2u would just be a vector that actually is twice as big, and so we would just get 6, 8. So we can take a vector, multiply it by a constant, whatever it is, and all you do is multiply. So let's say we now also have vector v, which is given by 5, -7. So we can add our vectors. We can do u plus v. And so to do this, we add the x numbers together, and then we add the y numbers together. So 3 plus 5 is 8. 4 plus the -7 will give us -3. So we have our adding. We can also do subtracting. So u minus v. So 3 minus 5, which is a -2. And then 4 minus a -7, which will give us 11. So we can add vectors, we can subtract vectors, we can multiply them by a constant, and so on. Well, let's say in terms now we have a plane that is traveling. So let's make a coordinate system. We got a plane that is traveling this way at 300 miles per hour. Also, there is a wind going like this at 60 miles per hour. Okay? So given that we have a 60 mile per hour wind that is blowing to the east, the plane is going at 300 miles per hour going due north, what would be the resultant vector given that now the plane is actually going to go like that, off of that. Okay. So we can find the magnitude of this. Again, basically this is a right triangle. And so the magnitude will be given by 300 squared plus 60 squared. Okay. So we can get that part. And so we can plug that one in. And when we do that, we end up, we're at basically 306 miles per hour. And we can also now get the angle that the plane is heading off at. And that would be given by 60 over 300. And do the inverse tangent of that. And we do that, we get 11.3 degrees. So if the plane actually wanted to go due north, it would actually have to fly 11.3 degrees this way. That way the wind would then give it its true north bearing that it would want. Right? So we have in terms of that. Right? We can also look what happened if we had not just in terms of something like this, but now we have in terms of this. We have a plane flies south at 150 miles per hour and encounters a wind blowing from the northeast at 40 miles per hour. Okay. So I want to know where, in terms of magnitude, what's going on, and what direction now is this plane taking off at. So let's first draw a picture. So it's flying south at 150 miles per hour. So let's say that this is my plane. A wind is blowing from the northeast, all right? So northeast, so you got north, south, east, west. So northeast would be a 45-degree angle, and blowing from the northeast, so it would be blowing like this. Okay. And then this is 40 miles per hour. Okay. So this angle right in here would be 45 degrees. Okay. So we can look in terms of my vectors in terms of the x and y components. So first off, for the plane, we have the x component and we have the y component. The plane has nothing in the x. It does have 150 in the y. Now for the wind. Well, the wind has an x and y component, and the x component will be given by 40 cosine, 45, and then 40 sine, 45. Right? So we can plug those two in. Right? And given that it is a 45-degree angle, both of these values will come out to be the same. So this will be 28.3. This will be 28.3. So now in terms of my totals, x total here is going to be 0 plus 28.3, so this is going to be 28.3. My y total is going to be 178.3. So now, in terms of the magnitude of this vector, it will be given by the square root of 28.3 squared, 178.3 squared. So we plug those in, and we find out that the magnitude of this vector will be 180.5. And then the angle it's going off at, theta. So theta is going to be the inverse tangent of y over x. So 178.3 and 28.3. And that gives us an angle of basically 81 degrees. So my resultant vector then is going to be like this. This angle is 81. And so in terms of my vector then, it has a magnitude of 180.5, and in terms of my angle, it would be 261 degrees. And so from here to there is 261. So we have in terms of vectors, have a magnitude, they have a direction. We can take vectors, we can add them, we can subtract them, we can multiply them together, and in terms of this one, we can find out where the plane is heading. The other section then for today deals with what are called parametric equations. So parametric equations are really equations that involve x, y, and t being a time component. So parametric. So involve x, y, and t. So a parametric equation would be something like this. X equals 3t plus 4, and y equals 2t minus 8. Right? That would be a parametric equation. So basically t would be time, and so we could look in terms of building a chart as to what's going on here. So we have in terms of t, we have in terms of x, we have in terms of y. So let's just do it for the first few numbers. Let's say 0, 1, 2, 3. So now what we're going to do is we're going to just take our numbers and we're going to plug them in. And so when t is 0, we got that x will be 4. And then when t is 0 here in my y equation, we got that y will be -8. And now when t is 1, we get 3 times 1, which is 3, plus 4, which is 7. And then here, 2 times 1 is 2. 2 minus 8 is -6. We can plug in our 2. 3 times 2 is 6. 6 plus 4 is 10. And then 2 times 2 is 4, minus 8 is -4. And then last we plug in our 3. 3 times 3 is 9, plus 4 is 13. And then 2 times 3 is 6, minus 8 is -2. So we have our information. So now we could actually now graph what's going on here. And when we graph it, we would only look and be concerned with my x and y part of this. And so we could do a quick graph. So let's say over 4, down 8, over 7, down 6, over 10, down 4, and then over 13, down 2. And we could then connect our dots, and we have what's going on with our parametric. The other thing with parametric equations then, and let's use this one still for this example, let's say I actually want to rewrite the equation in terms of x's and y's. So rewrite the parametric in terms of x and y. Right? So we start with these two, and so basically we need to pick one, whichever one we want, and we want to solve it for t. So let's take the bottom one. We got y equals 2t minus 8. Going to solve it for t, so let's add 8, add 8. So y plus 8 equals 2t. Last step, divide by 2. And so t is going to equal y over 2 plus 4. So now we can take that and we can substitute. Right? So we had our x equation, which was x equals 3t plus 4. We now know that t is given by this, and so we can take that and we will plug it in there for t. And so we get x is going to equal 3 times y over 2 plus 4 plus 4. And so now we go through and do this, we get x is going to equal 3y over 2 plus 12 plus 4. So x will equal 3y over 2 plus 16. So we have our equation now in terms of x and y's. So given a pair of equations, you should be able to rewrite it in terms of x's and y's. Well, in terms of example of parametric equations and where they are used and how they work, would be think in terms of physics and in terms of projectile motion. So we have a projectile, we launch it, and I want to know where is it in regards to its position. Right? And so in general, we got that x equals v naught cosine theta times t, and then y is going to equal v naught sine theta times t minus 4.9 t squared. And so this is based on metric system where gravity is 9.8, and we would get that. So for example, let's say now I have a projectile, and let's say that v naught is going to be 20 meters per second, and the launch angle is going to be 40 degrees. Okay? So now we can take that information and we can plug in and we can get where is my rocket, my projectile, over a time interval. So we would have x is going to be 40, is going to be 20 cosine 40 times t, and y is going to be 20 sine 40 times t minus 4.9 t squared. Again, that back term comes from gravity, because as soon as I launch it, gravity is going to want to be pulling my projectile down. So we can build our chart and see what's going on in terms of my position of my projectile over a given time interval. So we can get our chart. So first one, easy. When t is 0, well then this term will be 0, this term will be 0. So we got our projectile starting at basically ground level. So let's do when t is 2 seconds. So, and in 2 seconds time, we can figure out where our projectile is. So this will be 30.6. this will be 6.11. Okay. We do at 4 seconds. Yeah, this number comes out to be negative, which means I know it's already hit the ground for that part of it. And so for the other one, yeah, this is going to be 61.3. Right? So I know my rocket, my projectile will hit the ground somewhere in between 2 and 4 seconds. And we can figure out that number exactly because after all this is just a quadratic. And so we could solve that and get that number by setting my y equation equal to 0. So we can map out our projectile in terms of where it is over a given time frame. So roughly in terms of this projectile, what's happening, it starts here. At 2 seconds, it's up at 30. At 4 seconds, it's actually hit the ground, and we would get a projectile motion looking something like that in terms of what's going on with our projectile. So we have in terms of parametrics and mapping out what's going on with the motion of an object over a given time frame. And so with that, that will actually conclude this stuff for today.